Fam, what are these lighthouses saying?
Don't worry, bro. I brought the light and the torch.
A lie? Proper.
Are you dumb?
Use the Professor Camper's 3401. Wow.
Cool.
Wow. Awesome.
After initial testing,
We developed an advanced experimental testing apparatus.
a bookshelf with a hole in it.
The whole process begins with a string wound around a spool. The spool is connected to the very first gear, which drives the entire gear train. As the mass hooked up at the bottom of the string falls down, the first gear is driven. This driven gear drives the rest of the gear train, which has a 16-to-1 reduction. At the end of the gear reduction is a NEMA 17 synchronous motor. This motor, when driven backwards, acts as an AC generator. The AC current produced by the NEMA 17 is then rectified across a two-phase full-bridge rectifier. The rectifiers are connected in series. After the full-bridge rectifiers, they connect directly up to a supercapacitor that has a 20 farad 2.7 volt rating. Once the capacitor is sufficiently charged, which is after several drops, depending on how much it had been previously discharged, the circuit can be disconnected and used separately as a flashlight. Flip the switch on the circuit to power the LEDs, and the supercapacitor will allow current to flow through. Once the supercapacitor is drained, the LEDs will still run for a while on a dimmer setting. This light should be sufficient to navigate through the dark for several minutes, up to half an hour. We began our design process by determining that we wanted to produce electricity and identified campers as people who are off the grid with limited electricity needs. We found that the requirements consisted of cost, portability, and effectiveness. In terms of cost, we wanted to reduce the cost of parts and manufacturing. In portability, we wanted to reduce the size and the weight. And in effectiveness, we reduced the amount of energy required to input while producing enough energy as an output, or in other words, produced a reasonable efficiency. We tested numerous motors as generators, i.e. motors run backwards, to produce electricity, and identified the NEMA 17 as the best option. Based on its optimal efficiency RPM, we determined a torque that would be ideal for our application, based on the weight of the mass being used to generate. After determining the gear ratio, we made a CAD design and began manufacturing. Manufacturing consisted primarily of laser cutting HDF boards and assembled them by hand.
Based on a quasi-static assumption, using SolidWorks simulations, stresses and resultant displacements were determined for multiple gear models. Radial and tangential forces were applied based on a 4.5 kilogram mass suspended from a connected spool. With the bore fixed, simulations confirmed that the gear teeth with a pressure angle of 20 degrees would not fail. This was verified using experimental methods.
As a final overview, the potatoes drop down. They drive the motor powers the circuit, and the digital multimeter reads the voltage. Finally, we disconnect the circuit and turn on the light.